So what I want to tell you is on a much more local scale compared to the previous talk, which was very global, and now go back to France. And what I want to tell is about the impact of climate from historical periods on French crop production. And the motivation was this plot. The motivation was this plot. So when we look at growth rates of crop yield from 1900 until 2018, we can see that after World War II, crop growth was very high. So they grew with rates of 4 to 6% per year, which is unimaginable today because all the growth rates have declined. And for some crops like winter wheat, or also winter oats, they have even turned negative, meaning that crops have stagnated or even declined in growth. And that's a bit of a problem because for growing population and maybe even increasing demand for livestock, we need to grow more crops to sustainably feed it all. And the question is, where does the stagnation come from? So there's a lot of discussion in the literature where this could about possible reasons, and we asked whether it could already be due to observed climate change. And to answer this question, we used the concept of vulnerability, as it has been defined by the IPCC in the 5th assessment report. So it's a combination of exposure, sensitivity, and adaptive capacity. And exposure measures how often a crop experiences a dangerous climate regime, for example, very, very hot days in June. Then also how strongly a crop actually reacts to that dangerous climate regime. And finally, whether a farmer can still cope with this exposure and sensitivity, or is really doomed to experience yield losses. And here in this project, we did not consider adaptive capacity, but focused on the physiological dimensions, which is exposure to hazard and sensitivity. And similarly to what Johan just showed, it takes a lot of data before to start comprehensive analysis. And here I was lucky enough to receive from Philippe Sier one data set where one former colleague really drove around all the French departments and photocopied the ancient statistics books and manually copied the numbers by hand. And it was more than 300,000 data points manually copied by hand. So I'm lucky enough not having done this on my own, but I could make use of the data. And we had to clip the previous ones from 1900 because we didn't have the climate data, but we started around 1960, so the last 60 years. And we detrended yield data to not look at management and other improvement trends. We studied 11 crops, which have a major area share in France, and using Safran weather data and Merkur 2000 growing season data. So it's just a few of the details, which data sets we used. And importantly, we did not look at total yield anomalies, but we looked at yield losses. And so we said that anything which is 10% or more below expectations is a loss. So it has really repercussions for the farmers' economies or also for larger scale regional plannings. And since this talk or the whole session is about machine learning, I also have one slide on machine learning. And I used it more as a tool to select variables, because what we have is around 80 possible weather variables. For example, mean temperature in October, number of hot days in June, the precipitation in May, and all these variables going in, but I already know that most of them may have nothing to say for yield formation. And so we tried two different machine learning methods, random forest and lasso, which is a form of a linear regression that has a as a component within, not just to produce a model, but also to select important variables. And for all the 11 crops, I ran both models, and then I chose the one with the higher AUC, so the area under the curve, which is comparable to an R square, but for binary outcomes, so loss or no loss. And so the machine learning methods were not inspected further, they just helped me to select important variables. And then using these important variables, we started to define so-called hazards. And hazard from a risk perspective is an event. And if you enter that event, it becomes dangerous. And here the example is days above 30 degrees Celsius in July. And when you go from the left, which is 0 hot days, to the right, which is half of July is very hot, you can see that the fraction of observed yield losses increases. So the red circles are the observed losses, and the red line is the interpolation between them. The brown line is the so-called loss odds ratio that measures how likely a loss is actually compared to the background ratio of losses in the whole data set. And what we defined here is if you have a loss odds ratio of larger than 2, then you have a very high chance of observing a loss. And here it is the case that if you have more than 7.4 days above 30 degrees Celsius in June, you have pretty high chances of observing a yield loss. And so here we say that the hazard is more than 7.4 days above 30 degrees in June. So I hope that's clear. And so we use these two-step approaches. So first, variable selection by machine learning, and then a non-parametric hazard definition to study vulnerability. And so the main outcome is already written here, but I want to show a few slides before coming to that final result. So as Tom Henkel already pointed out, so random forests are not necessarily better than linear models. And so that's a whole bunch of numbers in the table for all the 11 crops. And what we did is also the full model and the out of sample model. And especially for the random forests, we can already see that the out of sample validation is crucial, because the full, when we supply the full data set to the random model, to the random forest, we always get the perfect fit. But if we do the out of sample validation, it's much lower. And often, or in 6 out of 11 cases, it's even beaten by a linear form, telling that the random forest is by far not generally better than a linear regression model. And now if we look at climate conditions in France since 1959, we can see that heat-related or high temperature-related hazards have increased. So when you just look at the very thick black line, there's a small dip around the 70s, but then you see a clear increase up to today. And the colored lines, the colored horizontal lines, they are the hazard thresholds for different crops. And for example, spring and winter wheat or sugar beet, they are very close to the observed temperatures already, meaning that the mean temperature in June is now very frequently crossing hazardous thresholds for several crops. And since the trajectory for temperature will very likely be upwards, we can conclude that the hazardous thresholds will be crossed much more often for more crops. And the same holds true for April. So we are also very close to crossing the hazardous thresholds for many crops. But interestingly, spring wheat, which is the orange line at the bottom, also has a low temperature hazard. So if it's too cold in April, there's also a danger of yield losses. And this hazard, luckily, we're going to evade in the future. And so I'm not sure how I'm doing it with time. Yeah, I think I can still show it. So, and here is maize. And what you see, that there are 16 different hazards. So if it's too hot in June, if it's too hot in July or August, if there are too many cold days in October, and so on from left to right. And you can see that for each of these hazards, you have a high chance of observing yield losses. They occur quite frequently, and they really induce several % of yield loss. So if weather is bad in one single month of the growing season, for example, if it's too hot and dry in June, it's very likely that the farmer may observe yield losses. So that's quite bad. But surprisingly and unexpectedly, if we combine all these hazards and look at it over different time frames, we can see that the so-called vulnerability, so that's the exposure and sensitivity and everything that I showed before, combined into one single number, it has decreased. So when you compare the turkey and the magenta bars, you can see that for all crops, vulnerability did not increase, at least, and for most of them, it did even strongly decrease. For example, for spring rape or potatoes, the vulnerability of these crops to climate hazards was much higher in the 30 years before today than in the 3 recent decades. And this is surprising because we would have expected, or at least I would have expected, that climate change or climate hazards have increased in taking toll of yield data, of yields, but the opposite seems to be the case. So that could be taken as a good message, as a nice message. But I would say we should beware of interpreting our results too optimistically, because as we've seen before, that heat-related hazards are rising strongly, and so they may change the picture completely, such that vulnerability has decreased from 1960s to 1990s, but then it rises again. And then compound hazards, so if there are 2 or more hazards occurring in one season, this may have large losses, so up to 50%. Then adaptive capacity is important. So for example, increasing irrigation if it's too dry, there are very clear limits. So this should also be considered. We did not include it in this study. Then if we say, okay, if there's more dry and hot spells over summer, we need to change crop breeding. But this is also quite well known that crop breeding is always much slower than the true hazards. And finally, an important point that there is a practical undersampling of theoretical climate variability. That means if we consider only 60 years, we have only 60 draws, but already the actual climate that we have, we could have seen several thousands of different realizations, so much more extreme or much more normal than what we have seen. So meaning that climate variability that we really did observe is not telling us enough variation to conclude on whether we are safe from climate or not. And actually, that's pretty much it. So what I learned is that the combination of machine learning and non-parametric approaches, which we used for the hazards, is useful. Then there's no clear preference of nonlinear. So random forest also tested extreme gradient boosting and neural networks. I didn't show it here, but they also are not clearly outperforming linear approaches. And the out-of-sample validation. Then hazards are very similar across time, crops, and regions. Surprisingly, the vulnerability of crops to climate has decreased, but there's still a good chance for bad prospect. And coming back on the original question, from this work, we cannot conclude that climate change has contributed to stagnation, but we would also not like to exclude this possibility. Yeah, and that's it. Thanks.
Thank you, Bernhard. If anyone has questions, we do have a few minutes before our next talk. I see that there's one in the question and answer worksheet, but you can also put them in the chat for now if you'd like. So in the Q&A worksheets, Lan Andin has asked if you can share your crop yield data sets of the 11 crops in France that you mentioned.
Yes, that's the idea. So we have this data since 1900. It will be published as a data descriptor. So all the 300,000 data points, hopefully early next year. And then it's all public.
There's another in the chat. Matthias Kunz asks, do you have another hypothesis why growth is decreased if it is not climate?
There are several theories. So especially for winter wheat, many people say that the physiological limit has been reached. So we cannot just go beyond 10 tons per hectare. But I think this is not the case because there are many farmers, many fields that reach much more, especially, for example, in Great Britain. So the physiological limit is likely not yet reached. Then it may be economic effects so that the farmer has no interest to increase yields even more because he would have to put so many more euros on the field to gain a few euros more in yields. But there's an economic trade-off. I think there were around 6 reasons. So we had a previous paper where we introduced this data set and where we discussed possible reasons for stagnation. I cannot recall them all at the moment, but the conclusion that we had based on the data is that we cannot find a good cause for we couldn't find any conclusive evidence for any of the 6 causes. So it's a bit elusive still, unfortunately.